We're going to start with a homework problem from assignment number 40. This was one of the homework problems, and several people asked me about the asymptote. Because when I drew the graphs for you, I usually put in the asymptote for you. And this one doesn't have the asymptote drawn in for you. But where would the asymptote go? You see where this flattens off? The asymptote would go in right here. So if they don't put the asymptote in for you, you have to look at the graph and figure out where it would go. The asymptote crosses the y-axis at 0. And then, is this an exponential growth or decay? This is going up. Is it growth or decay? It's going up. It's getting bigger. That's called growth. And all of this line is above the asymptote. The asymptote is at 0, so the range is y is greater than 0. Because it has arrows on the end, what is the domain? But this was a homework problem, and that wasn't an answer choice. All real numbers wasn't an answer choice in this multiple choice homework problem. So, first of all, does the domain go with the x or the y? And so when you have a domain question, any of the answer choices that have a y in it, you can mark those off. And so the correct answer choice looked like this. It had an x in it, and it went from negative infinity to positive infinity. If you go from negative infinity to positive infinity, wouldn't that include all of the numbers? So it's another way to write all real numbers. And the y-intercept was at positive 1. This was a word problem, and a lot of people missed it because they didn't make a good graph here. This population of Noahville, Texas is modeled by this exponential function where x is the number of years after 2014, and the graph is shown on the grid. The problem was they didn't make a good graph because this should have been an end point, and this should have been an arrow. So the arrow means it keeps getting bigger and bigger and bigger and bigger, right? And the end point is a little bit more than 40,000. And so this was the correct answer. Y is greater than or equal to 40,000. But because they didn't put the arrow on it like they were supposed to, a lot of people chose answer choice D, and that's really a mistake in the problem more than, hopefully, than a mistake of your understanding. But on this homework problem, it was question number 5, and it should have had an arrow on the end. The word exponential tells me that it keeps going up and up and up. Okay, now for our topic for today. Before we do our topic for today, though, we're going to go back. This is the exact table that we started with when we first started exponential functions. Would this be exponential growth or decay? It is growing. That means that if it is exponential, to get from one number to the next, you multiply. What is my multiplier here? To get from 1 to 5, what do I multiply? 5 to 25, what do I multiply? Times 5, times 5, times 5, times 5. And I could keep going. My equation for an exponential function is this, where A is the y-intercept and B is the multiplier. A is the y-intercept, B is the multiplier, X is the power. Now, A is 1 here. When you multiply by 1, does it get more or less or stay the same? Stays the same, right? When you multiply by 1. And so a lot of times when the A is a 1, we leave it out. It's not wrong to put it in there, but a lot of times we would just leave it out. And then we looked at this one. Again, what is the multiplier to go to the next number? 3 times what is 15? Well, it's 5 again, isn't it? 15 times 5. 75 times 5. And this is the y-intercept. So the equation would be because of order of operation, you can't multiply the 3 times the 5 and get a 15 because the 5 has an x power and the 3 does not. Sometimes you will see it written like this, because whether you write it like this or like that, the parentheses means multiply. So the parentheses can be on either one. Now, that's what we were doing with exponential functions. We're going to take exponential functions and look at them in a different way. Now, don't write this next screen down. Just look at it for a minute. We are going to look at what's called a geometric sequence. A geometric sequence is an exponential function. It's just a different way to look at it. Looking at it as an exponential function is the algebra way to look at it. Looking at it as a geometric sequence is the statistics way to look at it. But it's still the same pattern, because in either one, what do you do to get to the next number in the pattern? And when we had an exponential function, we called that multiplier. We either called it a multiplier or a growth factor. When it's a geometric sequence, we call that multiplier a common ratio. And this is what you need to write down. This is the geometric sequence rule. So write this down. So this is the rule for a geometric sequence, and the A1, the A sub 1 is how you say that, is the first number in the pattern. R is the multiplier, but when we have a geometric sequence, we call that multiplier a common ratio. N minus 1, N is the number of the pattern, and I'll show you what I'm talking about here in this next example. This is the same example that we were looking at back here on this screen. And I rewrote it over here. You don't have to copy the table down because you already did that. This is y equals 5 raised to the x power. So when we have a geometric sequence, do you see that that's the part we're looking at? When we have a geometric sequence, we do not look at the 0 term, the y-intercept term. We start with the first term. So, how do you use the rule? So, A sub n, I didn't find the multiplier. What is the multiplier here? I don't really have to find the multiplier because we already looked at that. We know that the multiplier is times 5. To get to the next number in the pattern, we multiply times 5. There's a lot of 5s in this problem. The first number is 5. The multiplier number is 5, and it's raised to the n minus 1. That's the sequence rule. I'll show you how to use the sequence rule in a minute. First, we're just going to write down the sequence rule. First number in the pattern, multiplier, n minus 1. Well, I guess I'll go ahead and tell you. So if I wanted to find the 10th number in the pattern, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I could multiply by 5 over and over and over again. Or I could use the rule. If I want to find the 10th number in the pattern, first number, multiplier, n minus 1. N is the number if I want to find the 10th term, n is equal to 10. But this doesn't say 10, this says n minus 1. What's 10 minus 1? This is always minus 1. And this is what I'm going to put in Desmos to figure out the answer. So and it's going to be huge, isn't it? I figured it out already. 5 times 5 raised to the 9th power. So if I multiplied by 5 over and over and over again, that would be the 10th number in the pattern. Sequence. This is the same pattern we did before. If you look at it from algebra, this is y equals 3, 5 to the x power. If you look at it from a statistics point of view, you're just looking at this much of the table. See, those are the same numbers. What was my multiplier to go to the next number? So this is going to be 5 to the n minus 1 because my multiplier was 5. Put it on my desk. And my first number in the pattern was a 15. So that is my geometric sequence rule. This pattern is called a geometric sequence because I multiply to get to the next number in the pattern. So on this next pattern, how do we figure out the multiplier? Well, if the multiplier is not obvious, the way you figure out the multiplier is you take the number and divide by the number in front of it. You take the 200 and divide by the number in front of it, which is 400. You take the 400 and you divide by the number in front of it. What do you get when you take 100 and divide by 200? What do you get when you divide 200 by 400? And that's why this is called a common ratio, because I got the same thing each time. That's what common means, the same thing. This fraction can also be called a ratio. So what is my multiplier? 0.5. Do we know that 0.5 is also equal to a half? So what's half of 100? That's the next number in the pattern. What's half of 50? And half of 25 is 12.5. So in this pattern, I'm multiplying by a half. That's why the numbers are going down, because I'm multiplying by a number less than 1. My common ratio is the multiplier, and that was a half. My starting number is 800. This is my geometric sequence rule. This example is a geometric sequence. It's a geometric sequence if you multiply to get to the next number in the pattern. Let's look at this pattern. To find out what the multiplier is, you take the 66 and divide by the number in front of it. 72 and divide by the number in front of it. 78 and divide by the number in front of it. When you divide, what do you get? 66 divided by 72 gives a decimal number. On my TI-83 calculator, if I push math, enter, enter, it changes that into a fraction. 72 divided by 78. If you click on the fraction button in Desmos, it changes to a fraction. I think it's easier to see what's going on here using fractions. Whether you're using fractions or looking at the decimal, did you get the same number every time? Or did you get a different number every time? It's a different number every time, so there is not a multiplier, so it is not a geometric sequence. To go from here to here, what would you actually need to do? Couldn't I subtract 6? If I go from here to here, couldn't I subtract 6 to get to the next number in the pattern? Is this a subtraction pattern instead of a multiplying pattern? What's 66 minus 6? Minus 6. Minus 6. This pattern is a subtraction pattern. It is not a geometric sequence. It's an arithmetic sequence. An arithmetic sequence is when you add or subtract to get to the next number. So we can't use our geometric rule on this because it's not geometric. To find out if this is a geometric pattern, a geometric sequence, you have to see if there's a common multiplier. So take the number and divide by the number in front of it. Even when you get to the 1/2, you still get the same multiplier number. A half divided by a fourth. What's my multiplier number? This number right here is called the common ratio. Common because they got the same thing every time. Ratio because ratio is another word for a fraction. But it's a multiplier. To get the next number in the sequence, 4 times 2 is 8. 8 times 2 times 2. The function rule would be the first number in the pattern times the multiplier times the n, raised to the n minus 1 power. This is the function rule for this pattern. I use the function rule for finding something like the 100th number in the pattern. I wouldn't want to multiply this out times 2 100 times, and so I could use the function rule and skip all the way down there. Is this a geometric sequence? If it's a geometric sequence, when I divide 16 by the number in front of it and 9 by the number in front of it, I have to get the same answer each time. So, what do I get when I divide 16 divided by 9? 16 divided by 9 is 1.7 repeating. 9 divided by 4. Did I get the same number in every time? I did not, so it is not a geometric sequence. Is there an adding number like there was on a previous pattern? Well, here it would be add 1, add 3, add 5. Am I getting the same number every time? It's not an adding pattern either. It is a pattern, however. Do you see the pattern? Anybody see the pattern? You know what I'm talking about when I say squared, when I say a number squared? 0 times 0 is still 0. 1 times 1 is 1. 2 times 2 is 4. 3 times 3 is 9. 4 times 4 is 16. 5 times 5 is 25. 6 times 6, 7 times 7. This is not a geometric pattern. It's not an arithmetic pattern. It is a pattern of perfect squares. So not all patterns are geometric or arithmetic. There are other kinds of patterns. But if I have a pattern, how do I find the pattern rule? Well, first, I need the multiplier. 56 divided by 28. 28 divided by 14. 14 divided by 7. When I divide that, I get the same number every time. The same multiplier number. If I have a multiplier, I'm multiplying by 2 to get to the next number in the pattern. Then I use this pattern rule. My multiplier number is 2. The first number in my pattern is 7. This is my geometric sequence rule. The first thing you do is find the multiplier. You take the 18 and divide by the number in front of it, 36 and divide by the number in front of it. If you get the same number every time, it is a geometric sequence, so you can use the geometric sequence rule. A sub 1 is the number you start with. This is the rule. Probably on a homework problem, I would write it this way instead. 0.5 is equal to a 1/2. So it could also be written in this form. You divide by the number in front of it to find out that the multiplier is 3. A sub n is 6. The common ratio is 3, n minus 1. This is my function rule. Now, how do I use the function rule to find the 15th term? If I am trying to find the 15th term, that's what the n stands for, the term I'm looking for. That's the 15th term, but what does it say right here? N minus 1. What is 15 minus 1? If I'm looking for the 15th term, I'm going to raise it to the 14th power because my equation says, or my rule says, n minus 1. So this part right here is what you put in Desmos or in a calculator to calculate the 15th term. Did you do it? It's a really, really big number. Did you get that really, really big number? To find the 15th term, does everyone understand why I put the 14 here? 15 minus 1 is 14. This is what you put in your calculator, and this great big huge number would be the 15th term, because when I'm multiplying 3 over and over and over again, the numbers get really, really big. On this example, I'm given a little bit different information. I'm not given the pattern. I'm given the numbers that plug into the function rule. A to the n equals the first number in the pattern. A1 means that's the first number in the pattern. R stands for common ratio. That means it's the multiplier. And the rule says I raise it to the n minus 1 power. This is my geometric sequence rule. I can use that rule to find the 5th number in the pattern. To find the 5th number in the pattern, I raise it to the 4th power, because this says n minus 1. If I'm looking for the 5th number, I raise it to the 4th power because the rule says I have to subtract a 1. So then you're going to put 288 parentheses 3 divided by 4 raised to the 4th power into your calculator. And the 5th term is going to be 91.125. Did you get that number when you put that into your Desmos or your calculator? Please copy this definition of a geometric sequence down into your notes.